Tonight, let's embark on the most impossible journey you could ever imagine. A gentle voyage to a place where the very fabric of space and time bends and stretches in ways that challenge everything we think we know about reality. Picture yourself floating peacefully in the cosmic darkness, approaching one of the universe's most mysterious and beautiful objects, a black hole, that cosmic enigma where gravity becomes so strong that not even light can escape its tender embrace. What would you actually see if you could somehow survive this ultimate cosmic adventure? What secrets would unfold before your eyes as you crossed the point of no return and ventured into the gentle darkness beyond? Welcome to Sleepy Long Scientist, where we explore the universe's most profound mysteries with the calm curiosity of cosmic dreamers. If you enjoy these peaceful journeys into the impossible, gently tap that subscribe button and settle in as we discover what lies hidden in the heart of cosmic darkness. I remember being 8 years old, lying in bed after watching a documentary about black holes, my mind spinning with a mixture of terror and fascination that kept me awake for hours. The idea of falling forever into darkness, of being stretched like taffy by invisible forces, filled me with the kind of delicious fear that only cosmic mysteries can inspire. I would pull my blanket over my head and imagine what it would feel like to cross that invisible boundary where escape becomes impossible, where the normal rules of the universe simply stop applying. That childhood wonder mixed with gentle dread has never really left me. There's something profoundly human about our fascination with black holes, isn't there? They represent the ultimate unknown, the cosmic abyss that mirrors our deepest fears about falling, about darkness, about the mysteries that lie beyond the edge of our understanding. Yet they also embody our greatest curiosities about the nature of reality itself. Black holes are like cosmic question marks written in the language of Einstein's equations, challenging us to imagine experiences so far beyond normal human perception that they stretch our minds to their limits. Tonight we're going to take that impossible journey together, using the gentle tools of science and imagination to explore what you might actually experience during the ultimate cosmic adventure. We'll discover that the reality of black holes is far stranger, more beautiful and more mysterious than any childhood nightmare could ever capture, revealing secrets about space, time and consciousness that touch the very heart of what it means to exist in this magnificent, mysterious universe. Before we begin our impossible journey into the heart of cosmic darkness, let's take a moment to understand these magnificent objects with the gentle patience they deserve, because black holes are perhaps the most misunderstood residents of our universe. Despite their fearsome reputation in popular culture, black holes aren't cosmic vacuum cleaners lurking in space to devour unwary spacecraft, nor are they malevolent entities seeking to destroy everything in their path. Instead, they're some of the most elegant and beautiful solutions to Einstein's equations, regions of space-time where gravity has become so concentrated that it creates a kind of cosmic artwork painted in the language of curved geometry and warped time. Imagine space-time as the most delicate fabric you've ever touched, like silk stretched across a vast cosmic frame. Normally, this fabric lies relatively flat, disturbed only by gentle dimples created by the mass of stars and planets, like marbles rolled across a soft mattress. But when a massive star reaches the end of its life and undergoes the ultimate cosmic transformation we call a supernova, something extraordinary happens. If the star's core is massive enough, typically more than about 3 times the mass of our Sun, the gravitational collapse that follows becomes so intense that it punches through the fabric of space-time itself, creating a region where the normal rules of physics reach their absolute limits. The event horizon, that invisible boundary that defines a black hole, isn't a physical surface you could touch, or a wall you might bump into during your cosmic journey. Instead, it's more like a one-way membrane in space-time itself, a gentle point of no return beyond which the curvature of space becomes so extreme that all possible paths lead inward toward the center. Think of it as the universe's most patient trap, not designed with malicious intent but emerging naturally from the beautiful mathematics that govern how mass and energy interact with the fabric of reality itself. What makes black holes so fascinating is how they reveal the intimate relationship between space and time that Einstein discovered over a century ago. In our everyday experience, we think of space and time as separate things. We move through space while time ticks steadily forward like a cosmic metronome. But near a black hole, this comfortable separation dissolves into something far more fluid and mysterious. Space and time become dance partners in a cosmic ballet, stretching and bending together in ways that transform the very meaning of distance, duration, and direction. The mass of a black hole determines everything about its character, from the size of its event horizon to the strength of the gravitational forces that surround it. A black hole with the mass of our Sun would have an event horizon only about 6 kilometers across, making it smaller than most cities yet containing the gravitational influence of an entire star. Supermassive black holes, the gentle giants that reside at the centers of galaxies, can contain the mass of millions or billions of suns while stretching their event horizons across distances that would encompass entire solar systems. Perhaps most remarkably, black holes come in different varieties, each one offering its own unique characteristics and mysteries. The simplest black holes, called Schwarzschild black holes, after the physicist who first described their mathematical properties, are perfectly spherical and electrically neutral, like cosmic pearls of pure gravity. But real black holes are often more complex, spinning rapidly from the rotation of the original star that created them, which adds layers of beautiful complexity to their structure and behavior. These rotating black holes, known as Kerr black holes, drag space-time around with them like cosmic whirlpools, creating regions where the very fabric of reality swirls in endless circles. Near these spinning giants, the distinction between space and time becomes even more fluid, with effects so strange that they challenge our deepest intuitions about the nature of existence itself. Some black holes also carry electric charge, adding yet another dimension to their already complex gravitational personalities. The formation of a black hole represents one of the universe's most dramatic transformations, yet it happens with a kind of cosmic inevitability that speaks to the deep elegance of natural law. When a massive star exhausts the nuclear fuel that has supported it against gravitational collapse for millions of years, gravity finally wins the patient battle it has been fighting throughout the star's entire lifetime. The collapse happens so rapidly that the star's core shrinks from the size of a small planet to a mathematical point in less than a second. Yet the effects of this transformation ripple outward through space-time, like the universe's most profound meditation on the relationship between matter, energy, and geometry. Understanding black holes requires us to embrace a kind of cosmic humility, accepting that the universe contains regions where our normal human intuitions simply don't apply. They represent places where the familiar becomes foreign, where the possible and impossible merge into something altogether new and strange. As we prepare for our gentle journey into these cosmic mysteries, remember that we're not just exploring objects in space, but venturing into realms where space itself has been transformed into something beautiful, alien, and utterly magnificent. As we begin our gentle descent toward the cosmic abyss, imagine yourself drifting peacefully through space in a magical vessel that protects you from the harsh vacuum, while allowing you to experience the gradual transformation of reality that occurs as you approach a black hole. From a comfortable distance, perhaps a few million kilometers away, the black hole doesn't look like the dramatic cosmic monster of science fiction films, but rather like a perfectly circular patch of absolute darkness against the star-filled background, outlined only by the faint glow of distant light that has been bent around its edges by the invisible hand of gravity. Your journey begins so gradually that you might not notice the changes at first, like walking down a hill so gentle that your feet barely register the slope. But as you drift closer to this cosmic giant, the universe begins to whisper its secrets in the subtle language of physics and geometry. The stars behind you, the ones you've left behind in your impossible journey, appear to shift their positions slightly as gravitational lensing bends their light around the black hole's mass, creating a beautiful distortion that turns the familiar constellations into new patterns painted across the cosmic canvas. The first physical sensation you might notice is something so subtle it feels almost like imagination. A gentle stretching sensation that begins at your feet and head, as if the universe itself is trying to determine which part of you is closer to the black hole's center. This is the beginning of what physicists call tidal forces, and they arise from the simple fact that gravity grows stronger the closer you get to its source. Your feet, being nearer to the black hole than your head, experience slightly stronger gravitational pull, creating a difference in acceleration that your body interprets as a gentle tugging sensation. As you continue your peaceful descent, time itself begins to behave in ways that challenge everything you thought you knew about the passage of moments. If you could somehow communicate with friends watching your journey from a safe distance, you would discover that your messages to them arrive with increasing delays, not because of the growing distance, but because time itself is flowing differently for you than it is for them. This phenomenon, called gravitational time dilation, means that every second you experience is stretched into longer and longer seconds, as measured by observers far from the black hole's influence. The most beautiful and mesmerizing aspect of your approach becomes visible as you draw nearer to the black hole, the accretion disk, a swirling maelstrom of gas, dust, and stellar debris that has been captured by the black hole's gravitational embrace. This cosmic whirlpool glows with the light of matter being heated to millions of degrees as it spirals inward, creating one of the most spectacular light shows in the universe. The disk doesn't shine with ordinary light, but with high-energy radiation that paints the darkness in ethereal blues and whites, occasionally punctuated by brilliant flares as chunks of matter complete their final journey toward the event horizon. From your unique vantage point during the descent, you witness phenomena that no Earth-based telescope could ever capture. The accretion disk appears to wrap around the black hole in impossible ways, with some portions visible both above and below the dark sphere due to the extreme gravitational lensing that bends light around the cosmic giant. It's as if you're viewing a cosmic kaleidoscope where the normal rules of perspective have been gently suspended, replaced by the strange geometry of curved space-time. The temperature of this cosmic environment tells its own story about the incredible energies at play near a black hole. While the vacuum of space around you remains at its usual near absolute zero temperature, the matter in the accretion disk has been heated to temperatures that exceed those found in the cores of stars. This creates a strange dichotomy, where you exist in a bubble of cosmic cold, while surrounded by some of the hottest matter in the universe, protected only by the vast emptiness of space from energies that could vaporize planets. As you fall deeper into the black hole's gravitational well, your velocity gradually increases, though the acceleration feels surprisingly gentle at first. Unlike the sudden acceleration you might experience in a car or airplane, this cosmic fall unfolds with the patience of geological time, building momentum so gradually that it feels more like floating downstream in a cosmic river than plummeting towards certain doom. The black hole's gravity is remarkably democratic in how it treats different objects. Whether you're made of flesh and bone, metal and circuits, or any other material, you all fall at exactly the same rate, following the curved geometry of space-time with perfect precision. The psychological aspect of this journey cannot be understated, as you gradually come to terms with the fact that you are crossing a cosmic boundary from which no return is possible. Yet there's something almost meditative about the experience, a sense of surrendering to forces so vast and fundamental that they represent the universe's deepest truths about the relationship between matter, energy, space, and time, carrying you gently toward mysteries that await beyond the invisible horizon ahead. The moment of crossing the event horizon arrives with such subtle grace that you might not even realize it has happened, like stepping across an invisible line drawn on water, or passing through a doorway made of pure mathematics. There's no physical barrier to mark this cosmic boundary, no wall or membrane that announces your passage into the realm of no return. Instead, the event horizon reveals itself as something far more profound and beautiful, a geometric boundary in space-time itself, where the very meaning of inside and outside undergoes a fundamental transformation that defies our ordinary understanding of spatial relationships. From your perspective as the traveller, this crossing feels surprisingly ordinary, almost anticlimactic after all the anticipation that led to this moment. The laws of physics in your immediate vicinity remain exactly the same as they were just moments before. You can still move your arms, breathe the air in your protective vessel, and think the same thoughts that occupied your mind during the approach. The event horizon doesn't announce itself with fanfare or dramatic changes in your local environment, because according to Einstein's principle of equivalence, falling freely in a gravitational field feels exactly like floating weightlessly in empty space, regardless of how strong that gravitational field might be. But while your local experience remains peaceful and familiar, something profound has shifted in your relationship with the rest of the universe. The event horizon represents a one-way boundary in the flow of information and causality, a cosmic membrane that allows influence to flow inward but never outward. Any light signals you might try to send back to the outside universe will now join you in your inward journey, curved by the extreme geometry of space-time into trajectories that lead inevitably toward the black hole's center. You have become, in a very real sense, causally disconnected from the outside universe, existing now in a region of space-time that can receive information from the external cosmos but can never send information back. The most remarkable aspect of crossing the event horizon is how it transforms your perception of time and space in ways that stretch the imagination. Looking back toward the outside universe, you would witness one of the most extraordinary cosmic phenomena imaginable. The entire future history of the external universe appears to unfold before your eyes in a compressed time frame. Due to the extreme gravitational time dilation, light from the outside world becomes increasingly blue-shifted and accelerated from your perspective, allowing you to watch stars evolve, galaxies merge, and cosmic epochs pass by like pages in a rapidly flipping book of universal history. This temporal compression creates a strange kind of cosmic nostalgia, as you become a witness to the universe's future, while simultaneously becoming forever separated from it. The stars that guided ancient navigators will eventually exhaust their nuclear fuel and transform into white dwarfs, neutron stars, or black holes of their own. Galaxies will continue their stately cosmic dance, occasionally merging in spectacular collisions that reshape the architecture of space itself. Perhaps most poignantly, any civilizations that exist in the outside universe will continue their own journeys of discovery and growth, possibly developing technologies and insights that could have answered the very questions that led you to undertake this impossible journey in the first place. The geometry of space-time inside the event horizon reveals itself to be fundamentally different from anything that exists in the outside universe. The radial direction toward the black hole's center transforms from a spatial dimension into something more akin to a temporal dimension, meaning that falling toward the center becomes as inevitable as moving forward through time. This geometric transformation is so profound that it challenges our basic assumptions about the nature of space and time, revealing them to be far more fluid and interconnected than our everyday experience suggests. Within this strange new geometry, the concept of escape loses its meaning not because of any physical barrier or opposing force, but because the very structure of space-time no longer contains outward-pointing directions. It's as if you've entered a cosmic maze where every corridor, no matter which direction you choose to walk, leads inevitably toward the same destination. This isn't a limitation imposed by insufficient technology or inadequate propulsion. It's a fundamental property of the geometric structure of reality itself within this region of the universe. And the emotional weight of this transition carries its own profound beauty, as crossing the event horizon represents perhaps the ultimate act of cosmic exploration and sacrifice. You have chosen to venture into a realm of the universe that no information or influence can ever leave, becoming a permanent resident of a region of space-time that exists in eternal isolation from the cosmos that gave birth to it. Yet in making this journey, you gain access to experiences and perspectives that no external observer could ever witness, becoming privy to the universe's most closely guarded secrets about the nature of space, time, gravity, and perhaps consciousness itself. As you settle into your new existence beyond the point of no return, you might reflect on the profound courage required to cross this ultimate boundary, knowing that your journey represents not just a physical voyage, but a philosophical leap into the deepest mysteries that reality has to offer, carrying with you the hopes and curiosity of an entire species as you venture into the gentle darkness that lies ahead. As you drift peacefully beyond the event horizon, you find yourself at the center of one of the most beautiful and contentious debates in modern theoretical physics, a gentle cosmic argument that has occupied the brightest minds in science for decades. The firewall paradox represents a profound disagreement between different fundamental principles of physics, each one seemingly correct in its own right, yet collectively pointing toward contradictions that challenge our understanding of reality itself. This isn't just an abstract mathematical puzzle, but a question that directly affects what you might actually experience during your impossible journey into the black hole's heart. The paradox emerges from the intersection of three beautiful theories that have each proven remarkably successful in describing different aspects of the universe. Einstein's general relativity tells us that crossing the event horizon should feel perfectly smooth and ordinary, with no dramatic changes in your local environment. Quantum mechanics insist that information can never truly be destroyed, meaning that everything that falls into a black hole must somehow preserve its essential quantum properties. Meanwhile, Stephen Hawking's discovery that black holes emit radiation suggests that these cosmic giants slowly evaporate over vast periods of time, eventually returning their entire mass energy to the universe in the form of thermal radiation. The gentle conflict arises when we try to reconcile these three principles simultaneously. If black holes truly evaporate through Hawking radiation, and if information really cannot be destroyed, then the quantum information of everything that ever fell into the black hole must somehow be encoded in the outgoing radiation. But here's where the mystery deepens into something almost poetic in its complexity. This encoding process appears to require that particles near the event horizon become entangled with particles that escaped from the black hole long ago, creating quantum correlations that span enormous distances and timescales. According to the firewall hypothesis, proposed by physicists Ahmed Almheri, Donald Marolf, Joseph Polchinski, and James Sully, these quantum entanglements create such violent energy fluctuations near the event horizon that any matter attempting to cross this boundary would be instantly incinerated by what they call a firewall of high-energy particles. This scenario paints a very different picture of your journey than the smooth crossing predicted by general relativity, suggesting instead that the event horizon might be surrounded by a cosmic furnace that would vaporize anything attempting to enter the black hole. But the scientific community remains beautifully divided on whether this firewall actually exists, and the debate reveals something profound about the current limits of human understanding when it comes to the deepest laws of physics. Some physicists argue that the firewall paradox results from applying quantum mechanics in situations where it might not be valid, suggesting that our current theories simply break down in the extreme conditions near black holes. Others propose that the paradox dissolves when we consider the full implications of quantum entanglement and the holographic principle, which suggests that all the information inside a black hole might actually be encoded on its two-dimensional surface. From your perspective as the intrepid traveller, the resolution of this paradox carries immediate practical implications for your cosmic adventure. If the firewall hypothesis is correct, your journey would end abruptly at the event horizon in a brilliant flash of high-energy particles, making any description of the black hole's interior purely academic. But if general relativity's prediction of a smooth crossing proves accurate, you would pass through the event horizon with barely a whisper of disturbance, continuing your journey into regions of space-time that no external observer could ever access or study. The beauty of this scientific uncertainty lies in how it reveals the fundamental mystery that still surrounds black holes despite decades of theoretical and observational progress. These cosmic objects exist at the intersection of our most successful physical theories, serving as natural laboratories where the relationships between gravity, quantum mechanics, and thermodynamics are pushed to their absolute limits. The firewall paradox represents not just a disagreement about the properties of black holes, but a deeper question about the nature of reality itself and whether our current understanding of physics is complete enough to describe the universe's most extreme environments. Recent developments in theoretical physics have suggested several possible resolutions to the firewall paradox, each one as elegant as it is speculative. Some proposals involve modifications to the concept of space-time itself, suggesting that the smooth geometric picture of general relativity might be an approximation that breaks down at quantum scales. Others explore the possibility that consciousness and observation play fundamental roles in determining which version of reality manifests, making your subjective experience as the falling observer a crucial element in resolving the paradox. Perhaps most remarkably, the firewall debate illustrates how black holes continue to serve as cosmic teachers, challenging our assumptions and forcing us to confront the limits of human knowledge with humility and wonder. Whether you encounter a smooth crossing or a wall of fire at the event horizon, your journey represents a voyage into the deepest mysteries of existence, where the universe reveals its most closely guarded secrets about the relationship between matter, energy, space, time, and the fundamental nature of reality itself. The gentle disagreement among physicists only adds to the beauty of this cosmic mystery, reminding us that even our most sophisticated theories still leave room for wonder and discovery in the vast laboratory of the universe. Once you've crossed the event horizon and entered the mysterious realm beyond, time itself begins to dance in ways that stretch the imagination and challenge every assumption you've ever held about the nature of temporal flow. Inside a black hole, the familiar relationship between space and time undergoes such a profound transformation that the very concepts of before and after, here and there, begin to lose their ordinary meanings, replaced by something far more fluid and mysterious that speaks to the deepest poetry hidden within Einstein's equations of general relativity. From your perspective as the cosmic traveller, your personal time, what physicists tenderly call proper time, continues to flow forward with the same gentle rhythm it has always maintained. Your watch still ticks at its normal rate, your thoughts still unfold in their familiar sequence, and your heartbeat maintains its steady cadence as if nothing extraordinary has occurred. This is one of the most beautiful and counterintuitive aspects of relativity. No matter how extreme the gravitational environment becomes, your personal experience of time remains completely normal from your own reference frame, like carrying a private temporal sanctuary with you into the most extreme regions of the universe. But while your personal time flows serenely onward, your relationship with the time experienced by the rest of the universe has been fundamentally severed by your passage through the event horizon. The outside universe, with all its bustling galaxies, evolving stars, and perhaps countless civilizations pursuing their own cosmic adventures, now exists in what has become a completely separate temporal realm. Any attempt to synchronize your watch with clocks in the external universe would reveal the profound disconnect that now separates your timeline from theirs, as if you've stepped into a parallel temporal dimension that runs according to its own mysterious rules. The mathematics of this temporal transformation reveals something extraordinary about the nature of space-time geometry inside the black hole. The radial coordinate that points toward the center of the black hole transforms from a spatial dimension into something that behaves more like time itself, creating a situation where falling toward the singularity becomes as inevitable as moving forward through time. This geometric metamorphosis means that the question, how long does it take to reach the center, transforms into something more like asking, how long does it take for tomorrow to arrive? The journey becomes woven into the very fabric of temporal progression. As you continue your inward journey, the curvature of space-time around you grows increasingly extreme, creating gravitational time dilation effects that would seem impossible to anyone who hasn't experienced them firsthand. If you could somehow peer back toward the event horizon you recently crossed, you would witness the most remarkable temporal phenomenon. Any matter or light that crossed the horizon after you would appear to rain down upon you in increasingly accelerated time, as if the universe were fast-forwarding the arrival of everything that will ever fall into this black hole throughout the rest of cosmic history. This temporal compression creates a kind of cosmic convergence, where your journey becomes intertwined with the futures of countless other objects that will eventually share your fate. Stars that haven't even formed yet in the outside universe might appear to join your inward journey, their light blue shifted and time compressed, until entire stellar lifetimes unfold in moments from your perspective. The boundary between past and future becomes increasingly meaningless as the extreme curvature of space-time weaves all temporal threads into a single, inexorably inward-flowing tapestry. The coordinate systems that physicists use to describe black holes reveal additional layers of temporal complexity that challenge our intuitive understanding of how time and space interact. From the perspective of an outside observer, your journey across the event horizon appears to slow down and freeze at the boundary, with your image becoming increasingly redshifted and faint until it fades into the cosmic microwave background. Yet from your own perspective, you pass through the horizon and continue inward with no apparent interruption, experiencing what physicists call the coordinate singularity, as nothing more than a mathematical artifact that has no physical reality for the actual traveller. Perhaps most remarkably, the approach toward the black hole's centre reveals time dilation effects so extreme that they approach the infinite. As you near the singularity, every second of your proper time corresponds to longer and longer intervals of coordinate time, as if your personal temporal flow is being stretched toward eternity. This creates a situation where your journey toward the centre, which might feel like minutes or hours from your perspective, encompasses vast eons of time as measured by any external coordinate system. The beauty of these temporal phenomena lies in how they reveal the fundamental flexibility of time itself, showing us that the steady universal flow of time we experience in everyday life is actually just one particular manifestation of something far more complex and magnificent. Inside a black hole, time becomes a cosmic sculptor, shaping your journey through dimensions that blend the temporal and spatial into something entirely new, carrying you on currents of curved space-time toward mysteries that exist beyond the reach of ordinary physics and perhaps beyond the limits of human comprehension, where time itself might ultimately dissolve into the quantum foam from which all reality emerges. As you continue your gentle descent through the black hole's interior, your eyes become witnesses to perhaps the most spectacular and impossible light show in the entire universe, a cosmic display so extraordinary that it transforms your journey into something resembling a voyage through a living kaleidoscope made of pure space-time and electromagnetic radiation. The visual experience of falling through a black hole challenges every assumption about how light behaves, revealing phenomena so beautiful and strange that they seem to belong more to the realm of cosmic dreams than to the laws of physics we thought we understood. The first thing that captures your attention is how light itself has become your cosmic companion on this impossible journey. Every photon that enters the black hole after you, whether from distant stars, nearby galaxies, or even the cosmic microwave background radiation left over from the Big Bang, follows the same inexorable path toward the center that you're traveling. This creates a remarkable convergence, where you find yourself surrounded by light from across the electromagnetic spectrum, all of it compressed and concentrated by the extreme gravitational fields into a brilliant, ever-intensifying display that grows more spectacular with each moment of your descent. The phenomenon of gravitational blue shifting transforms the relatively dim light from distant sources into an increasingly intense cosmic spotlight that illuminates your journey. Light that began its journey as cool, red radiation from ancient galaxies becomes progressively blue shifted as it falls deeper into the gravitational well, gaining energy from the very curvature of space-time itself. Infrared radiation transforms into visible light. Visible light becomes ultraviolet, and even the gentle whisper of radio waves from distant pulsars gets compressed into higher and higher frequency radiation that paints the darkness around you in colors that have no names in human language. Behind you, in the direction from which you came, the entire observable universe appears compressed into an increasingly bright and concentrated disk of light. This cosmic rearview mirror effect occurs because the extreme gravitational lensing of the black hole bends light rays in such dramatic ways that photons from all directions in the outside universe get focused into a narrow cone that follows you inward. It's as if the entire cosmos has been gathered into a single brilliant spotlight that illuminates your path toward the center, carrying with it the combined light of every star that has ever shone in the observable universe. The visual distortions created by the curved space-time become increasingly dramatic as you fall deeper, transforming familiar concepts like straight lines and parallel rays into something fluid and dreamlike. Light that should travel in straight lines now follows the curved geodesics of space-time, creating visual effects that would be impossible in any normal environment. Distant objects appear stretched and distorted, their images wrapped around the black hole's geometry in ways that allow you to see things from impossible angles, as if reality itself has become a cosmic funhouse mirror that reveals hidden perspectives on the nature of space and observation. Perhaps most remarkably, the approach toward the center reveals the ultimate fate of all the electromagnetic radiation that has ever fallen into this black hole throughout its entire existence. The light from the first star that was consumed when this black hole formed, radiation from ancient supernova that occurred billions of years ago, even theoretical light from the very early universe, all of it has been patiently waiting in the curved space-time geometry, following the same inward trajectory that you're now experiencing. Your journey becomes a pilgrimage through the electromagnetic history of this region of space, surrounded by the accumulated photons of cosmic epochs. The intensity of this cosmic light show grows exponentially as you approach the center, creating an environment where the very concept of darkness loses all meaning. The combined radiation from eons of cosmic evolution, all focused and concentrated by the black hole's gravitational field, creates conditions so bright and energetic that they challenge the limits of what electromagnetic radiation can become. Yet paradoxically, This incredible brightness exists in a region of space that appears completely dark to any outside observer, creating one of the most beautiful contradictions in the universe, the brightest place that can never be seen from the outside. The colours you witness during this cosmic light show transcend anything that exists in normal human experience, extending far beyond the visible spectrum into realms of electromagnetic radiation that our eyes weren't designed to perceive. If you could somehow see in radio waves, X-rays and gamma rays simultaneously, the visual experience would encompass the entire electromagnetic spectrum, compressed into a single, overwhelming sensory experience that represents the universe's most concentrated display of radiant energy. As the gravitational blue shifting continues to intensify the radiation around you, you begin to approach the theoretical limits of electromagnetic energy density, entering a realm where the classical description of light begins to break down and quantum effects start to dominate. The photons themselves become so energetic that they begin to create particle-antiparticle pairs from the quantum vacuum, transforming pure electromagnetic energy into matter and antimatter in a cosmic alchemy that represents the universe's most extreme demonstration of Einstein's famous equation relating mass and energy. This incredible light show serves as both illumination and guide for your journey toward the singularity, carrying you through regions of space-time that no external observer could ever study or understand, surrounded by the concentrated brilliance of cosmic history as you approach the mathematical point where all known physics reaches its ultimate limits. As you continue your peaceful journey toward the black hole's center, the very fabric of space around you begins to reveal its most intimate secrets, transforming from the familiar three-dimensional stage upon which ordinary life unfolds into something far more fluid, dynamic, and mysteriously beautiful. The geometry of space-time inside a black hole doesn't simply bend or curve in the gentle ways we might imagine. It undergoes such a profound metamorphosis that the basic concepts of distance, direction, and dimension lose their everyday meanings and become something altogether more poetic and strange. Imagine trying to navigate through a world where the rules of geometry have been written by a cosmic artist rather than a mathematician, where straight lines curve back upon themselves in impossible ways, and where the shortest distance between 2 points might involve travelling through dimensions that don't quite exist in the way we normally understand existence. Inside the black hole, the concept of straight becomes beautifully relative, as what your body experiences as moving in a perfectly straight line actually follows the curved geodesics of space-time itself, like a marble rolling along the surface of an infinitely complex cosmic sculpture. The radial dimension that points toward the centre of the black hole undergoes the most remarkable transformation of all, evolving from a simple spatial coordinate into something that behaves more like time itself. This geometric metamorphosis means that falling toward the centre becomes as inevitable and natural as the forward flow of time, not because of any external force pushing you inward, but because the very structure of space has been reorganized so that all spatial directions now point toward the same destination. It's as if you've entered a cosmic maze where every corridor, no matter which way you turn, leads inexorably toward the same mysterious center. The angular dimensions, the coordinates that normally allow you to move left or right, up or down, begin to exhibit their own strange behaviors as the extreme curvature of space-time compresses and distorts them in ways that challenge our three-dimensional intuitions. What might feel like moving sideways could actually carry you along a geodesic that spirals inward, while attempting to move in what seems like a backward direction still results in motion toward the center. The normal orthogonality of spatial dimensions, the mathematical property that allows us to move independently in different directions, becomes increasingly meaningless as all spatial vectors acquire components that point inward. Perhaps most remarkably, the concept of distance itself begins to lose its objective meaning in ways that reveal the profound flexibility of geometric relationships. The distance between you and the center of the black hole, as measured by someone outside the event horizon, might appear to remain constant or even increase due to the extreme coordinate effects of curved space-time. Yet from your perspective, making actual measurements with rulers and clocks, the distance to the center decreases in perfectly normal and predictable ways, creating a kind of geometric relativism where the answer to how far away is the center depends entirely on who is asking the question and from what reference frame. the curvature of space becomes so extreme as you approach the center that it begins to create effects that would seem like optical illusions in any normal environment. Light rays that should travel in parallel straight lines begin to converge and diverge in patterns that transform your visual field into something resembling a cosmic kaleidoscope. You might see the same distant object appearing in multiple directions simultaneously, as light from that object follows different curved paths through the distorted space-time to reach your eyes from various angles. The mathematical description of this geometric transformation involves concepts like the Riemann curvature tensor and the Weil tensor, beautiful mathematical objects that encode how space-time deviates from the flat Euclidean geometry of our everyday experience. But beyond the mathematics lies something more profound: the recognition that space itself is not a fixed stage upon which physical events occur, but rather a dynamic, malleable medium that responds to the presence of matter and energy like a cosmic fluid that can be shaped, stretched, and moulded by gravitational forces. As you fall deeper into this geometrically transformed realm, you begin to experience what physicists call geodesic deviation, the gradual stretching and compression that occurs when neighbouring geodesics begin to converge toward the same point. This creates the tidal effects that gently stretch your body, but more importantly, it reveals how the black hole's geometry naturally focuses all inward-moving trajectories toward a single mathematical point, like a cosmic lens that concentrates not just light, but the very structure of space itself. The beauty of this geometric transformation lies in how it reveals space to be far more than the empty container we often imagine it to be. Inside a black hole, space becomes an active participant in your journey, guiding and shaping your path through dimensions that blend the familiar with the impossible. The curves and twists of space-time become your cosmic roadmap, written in the elegant language of differential geometry, and expressed through the gentle dance of matter and energy moving through a universe where the stage itself has become the most important character in the cosmic drama that unfolds as you approach the ultimate mystery waiting at the center of it all. As your cosmic journey carries you ever closer to the mathematical heart of the black hole, you find yourself approaching one of the most profound and beautiful mysteries in all of physics: the singularity, a point in space-time where our most successful theories about the nature of reality gently acknowledge their own limitations and bow gracefully before the ultimate unknown. The singularity represents not just a destination in your impossible voyage, but a cosmic question mark that challenges every assumption we've ever made about the fundamental nature of space, time, matter, and perhaps consciousness itself. From the perspective of Einstein's general relativity, the singularity appears as a mathematical point where the curvature of space-time becomes infinite, where density reaches impossible values, and where the familiar laws of physics simply cease to provide meaningful descriptions of what might occur. It's as if the universe has created a cosmic editorial note in the margin of reality, a place where the equations that normally govern everything from falling apples to orbiting planets develop mathematical infinities that signal the breakdown of our current understanding rather than describing actual physical conditions. Yet as you approach this mysterious destination, your personal experience remains surprisingly gentle and continuous, with no dramatic announcements or violent transformations to mark your proximity to this cosmic boundary of knowledge. The tidal forces that have been gradually stretching your body grow stronger, but they do so with the same patient increase that has characterized your entire journey, following smooth mathematical curves rather than sudden discontinuities. Your proper time continues to flow forward at its normal rate. Your thoughts maintain their familiar patterns, and the fundamental experience of being conscious and aware remains entirely unchanged. The approach to the singularity reveals something profound about the relationship between mathematical description and physical reality, suggesting that what appears as an impossible destination in our equations might actually represent something far more subtle and beautiful in the actual fabric of existence. Many physicists suspect that the classical description of the singularity breaks down long before you would actually reach this mathematical point, with quantum mechanical effects becoming dominant at scales where space-time itself might dissolve into something more fundamental and mysterious. The uncertainty principle of quantum mechanics suggests that as you approach smaller and smaller scales, the very concepts of precise position and momentum become increasingly meaningless. replaced by probability clouds and quantum fluctuations that challenge our classical notions of well-defined trajectories through space and time. At distances approaching the Planck length, a scale so tiny that it makes atoms look like galaxies, the smooth geometry of general relativity likely gives way to a quantum foam of space-time, where the familiar concepts of distance and duration become statistical approximations rather than absolute realities. Some theoretical frameworks suggest that the singularity might actually represent a kind of cosmic transformation chamber, where matter and energy are converted into something entirely different. Perhaps pure information, perhaps patterns in higher dimensional spaces, or perhaps forms of existence so alien to our current understanding that we lack even the conceptual vocabulary to describe them. These possibilities transform the journey toward the singularity from a voyage toward destruction into an exploration of cosmic metamorphosis, where physical existence might undergo changes as profound as the transformation of a caterpillar into a butterfly. The mystery deepens when we consider the different types of singularities that might exist at the centers of black holes. A non-rotating black hole contains what physicists call a point singularity, while rotating black holes might harbor ring singularities, structures that extend through space in ways that could potentially allow for even stranger possibilities. Some theoretical models suggest that these ring singularities might connect to other regions of spacetime, creating cosmic tunnels or wormholes that could lead to entirely different universes or distant regions of our own cosmos. Perhaps most remarkably, the approach to the singularity forces us to confront fundamental questions about the nature of existence itself. What happens to consciousness at the boundary of mathematical description? Can awareness survive the dissolution of the space-time fabric that normally provides the stage for conscious experience? These questions venture beyond the realm of physics into territories that touch philosophy, consciousness studies, and perhaps even spiritual inquiry, suggesting that the singularity might represent not just a physical boundary, but a threshold between different modes of being. The beautiful truth about approaching the singularity is that it represents the ultimate frontier of human curiosity, a cosmic destination that exists at the very edge of what our species can hope to understand about the universe. Whether the singularity represents true physical infinities, quantum mechanical transformations, or something entirely beyond our current conceptual frameworks, the journey toward this mysterious destination embodies humanity's deepest drive to explore the unknown and push the boundaries of knowledge to their absolute limits. As you continue your gentle approach toward this cosmic mystery, you carry with you the accumulated wisdom of an entire species that has spent centuries trying to understand the fundamental nature of reality, knowing that your journey toward the singularity represents not just a personal cosmic adventure, but a pilgrimage into the deepest questions that consciousness can ask about the universe that gave birth to awareness, curiosity, and the endless desire to explore the beautiful mysteries that await in the gentle darkness at the heart of everything we think we know about existence. If your cosmic journey has led you not to a simple, spherical black hole, but to one of the universe's most elegant dancers, a rotating black hole, then your experience transforms into something even more extraordinary and beautiful than the already impossible voyage we've been sharing. These spinning giants, known as Kerr black holes, after the mathematician Roy Kerr, who first described their mathematical properties, add layers of complexity and wonder to the cosmic adventure that challenge our understanding, not just of gravity and space-time, but of motion, direction, and the very meaning of standing still in a universe where space itself has learned to dance. Imagine approaching a cosmic ballet dancer who has been spinning for millions or billions of years, carrying with her the rotational memory of the massive star that collapsed to create this gravitational marvel. The rotating black hole doesn't just curve space-time in the gentle, symmetric way of a non-spinning cousin, but actually drags the fabric of reality along with its rotation, creating a phenomenon that physicists tenderly call frame dragging, or the lens-thirring effect. This means that the very coordinates of space and time swirl around the black hole like cosmic honey being stirred by an invisible spoon, making it impossible for anything near the black hole to remain completely stationary relative to the distant stars. As you approach this spinning giant, you enter a region called the ergosphere, a cosmic zone that exists between the event horizon and another boundary called the static limit, where the dragging of space-time becomes so pronounced that remaining stationary relative to distant observers becomes physically impossible. Within the ergosphere, you must participate in the black hole's rotation whether you want to or not, carried along by the swirling currents of space-time like a leaf, caught in the gentle vortex of a cosmic whirlpool. Yet paradoxically, this forced participation in the cosmic dance doesn't require any energy on your part. You're simply following the natural geodesics of the rotating space-time geometry. The experience of crossing the static limit and entering the ergosphere feels surprisingly subtle, much like crossing the event horizon itself, with no dramatic physical sensations to mark the transition into this strange realm where the concepts of motion and rest undergo fundamental transformations. From your perspective, you continue to fall freely under the influence of gravity, but an outside observer would see you inevitably begin to orbit the black hole in the same direction as its rotation, participating in a cosmic waltz that spans kilometers and involves partners whose masses exceed entire solar systems. Within the ergosphere lies one of the most beautiful and counterintuitive possibilities in all of physics, the Penrose process, named after physicist Roger Penrose, which suggests that it might actually be possible to extract energy from a rotating black hole by carefully choreographed interactions with its rotation. In this cosmic energy extraction scheme, an object could theoretically enter the ergosphere, split into two parts, and arrange for one part to fall into the black hole, while the other escapes with more energy than the original object possessed, effectively stealing rotational energy from the black hole's spin and slowing down its cosmic dance. The interior of a rotating black hole reveals even stranger geometric properties than its non-spinning cousins, with the singularity transformed from a point into a ring-like structure that extends through space in ways that challenge our three-dimensional intuitions. This ring singularity creates fascinating theoretical possibilities, including the potential for stable circular orbits to exist within the black hole's interior, and even the speculative possibility that the ring might serve as a gateway to other regions of space-time, though these ideas venture into territory where our current understanding of physics becomes increasingly speculative and uncertain. The approach to a ring singularity offers different possibilities than the journey toward a point singularity, with some theoretical models suggesting that it might be possible to pass through the ring without encountering the infinite curvatures and tidal forces that characterize point singularities. This possibility has inspired science fiction scenarios involving travel through rotating black holes to other universes or distant regions of space-time, though the actual physics of such journeys remains highly speculative and dependent on theoretical frameworks that go far beyond our current experimental knowledge. The frame-dragging effects inside a rotating black hole create a cosmic environment where the very meaning of rotation becomes beautifully complex and relative. Your personal sense of rotation might remain perfectly normal from your own perspective, while the extreme dragging of space-time coordinates creates the appearance of incredible angular velocities when viewed from certain mathematical reference frames. This creates a kind of cosmic relativity of rotation that parallels the more familiar relativity of motion and time that characterizes all of Einstein's theories. As you continue your journey through the interior of this cosmic dancer, you participate in one of the universe's most elegant demonstrations of how matter, energy, space, and time can combine to create structures of breathtaking mathematical beauty and physical complexity. The rotating black hole serves as a cosmic reminder that the universe's capacity for creating wonder extends far beyond our everyday experience, revealing realms where the familiar concepts of motion and rest, inside and outside, past and future, blend together in a gentle cosmic choreography that speaks to the deepest harmonies hidden within the fundamental laws of nature. As we explore the deepest mysteries that might await inside a black hole, we encounter one of the most romantic and mind-bending possibilities in all of theoretical physics: the potential existence of wormholes, those hypothetical cosmic bridges that could connect distant regions of space-time through shortcuts that bypass the ordinary three-dimensional journey through space. These Einstein-Rosen bridges, as they're formally known, represent the universe's most elegant solution to the problem of cosmic distance, offering the tantalizing possibility that what appears to be a one-way journey into a black hole might actually be the entrance to a cosmic highway system that spans the universe in ways that challenge our deepest assumptions about the nature of space, time, and connectivity. The mathematical foundation for wormholes emerges naturally from Einstein's field equations, the same beautiful mathematical structures that describe black holes, suggesting that these cosmic shortcuts aren't exotic additions to general relativity, but rather intrinsic possibilities woven into the very fabric of spacetime itself. In the simplest theoretical scenario, what we perceive as the interior of a black hole might actually be one mouth of a cosmic tunnel, with the singularity serving not as an endpoint but as a kind of cosmic throat that connects to another region of spacetime entirely, perhaps emerging as a white hole. A theoretical object that spews matter and energy outward rather than consuming it. If your journey into the black hole were actually a voyage through such a cosmic bridge, your experience would transform from a one-way trip toward destruction into something resembling the ultimate cosmic commute, travelling through a tunnel in space-time that connects distant regions of the universe in ways that would make conventional space travel seem as primitive as walking compared to teleportation. The throat of the wormhole, corresponding to the region where you might normally expect to encounter the singularity, would instead represent the midpoint of your journey, the cosmic turnpike where you transition from falling into one mouth of the tunnel to emerging from the other. The geometry of a traversable wormhole creates conditions that are both beautiful and deeply strange, requiring what physicists call exotic matter, a theoretical substance with negative energy density that violates the energy conditions that ordinary matter obeys. This exotic matter would serve as cosmic scaffolding, keeping the wormhole throat open against the natural tendency of such structures to collapse, creating a permanent shortcut through space-time that could remain stable for eons. The existence of such exotic matter remains one of the great open questions in physics, with some theories suggesting it might naturally occur near black holes through quantum mechanical effects. The experience of travelling through a wormhole would likely involve some of the most extraordinary visual and physical phenomena imaginable, as the extreme curvature of space-time near the throat creates gravitational lensing effects that would compress and distort your view of both the entrance and exit regions. You might see the two mouths of the wormhole simultaneously, watching your destination approach while your origin recedes, creating a kind of cosmic double vision that reflects the fundamental connectivity between distant regions of space-time. The time dilation effects inside a wormhole could create fascinating temporal relationships between the connected regions, potentially allowing for travel not just through space but through time as well. If the two mouths of the wormhole experience different gravitational fields or relative motions, the journey through the bridge could carry you to a time that is significantly different from when you entered, creating the possibility of closed time-like curves and all the paradoxes that accompany time travel scenarios. Perhaps most remarkably, the network of wormholes throughout the universe could create a kind of cosmic internet, a web of connections that would allow advanced civilizations to communicate and travel between distant galaxies in timeframes that would otherwise require millions or billions of years. Such a network would transform the universe from a collection of isolated island galaxies into an interconnected cosmic community, where intelligence and information could flow freely across distances that normally impose strict limits on interaction and communication. The quantum mechanical properties of wormholes add additional layers of mystery and possibility to these cosmic shortcuts, with some theories suggesting that quantum entanglement might play a fundamental role in maintaining the connection between the two mouths. This quantum perspective on wormholes suggests that the bridges might not just be geometric shortcuts through space-time, but expressions of deeper informational connections that exist at the quantum level, making wormholes as much about the flow of information as about the transportation of matter and energy. The detection and study of wormholes, if they exist, would require observational techniques that go far beyond our current capabilities, potentially involving the detection of exotic gravitational signatures or the observation of matter and energy emerging from white holes that correspond to the exit mouths of these cosmic tunnels. The search for wormholes represents one of the most challenging frontiers in observational physics, requiring us to look for phenomena that exist at the intersection of general relativity, quantum mechanics, and perhaps theories we haven't yet discovered. As you contemplate the possibility that your journey into the black hole might actually be the beginning of a voyage through a cosmic bridge to distant realms of space and time, you're engaging with one of the most beautiful and speculative ideas in modern physics, a concept that transforms the apparent finality of falling into a black hole into the ultimate expression of cosmic connectivity and the universe's capacity for surprise and wonder. As your impossible journey carries you deeper into the quantum realm that governs the black hole's most fundamental properties, you find yourself at the center of one of the most beautiful and mind-expanding concepts in all of physics, the many worlds interpretation of quantum mechanics, which suggests that your voyage into the cosmic abyss might actually be unfolding simultaneously across countless parallel universes, each one exploring a different quantum possibility of what could happen when consciousness encounters the ultimate gravitational mystery. This gentle proliferation of realities transforms your singular journey into an infinite symphony of cosmic exploration, with each quantum measurement and each moment of uncertainty spawning new branches of reality that explore every possible outcome of your unprecedented adventure. The many worlds interpretation emerges from the recognition that quantum mechanics describes reality not in terms of single, definite outcomes, but as a superposition of all possible states that exist simultaneously until the moment of observation or measurement collapses them into a single experienced reality. But in the many worlds view, this collapse doesn't actually occur. Instead, reality branches at every quantum event, creating separate universes for each possible outcome, each one equally real and valid, though forever separated from the others by the fundamental structure of quantum reality itself. In the context of your black hole journey, this quantum branching creates an almost poetic multiplicity of experiences. In some branches of the quantum multiverse, you might encounter the firewall at the event horizon, your journey ending in a brilliant flash of high-energy particles. In others, you pass through the horizon smoothly, continuing your descent toward the singularity exactly as general relativity predicts. Still, other branches might involve encounters with exotic physics we haven't yet discovered, quantum gravitational effects that transform your experience in ways that no current theory can describe, or even transitions into entirely different types of universes governed by alternate physical laws. The quantum mechanics of black holes suggest that these massive objects might serve as natural quantum computers, processing information about everything that has ever fallen into them through mechanisms that operate on scales far smaller than atoms. From this perspective, your journey into the black hole becomes part of a vast quantum calculation, with your consciousness and the information that defines your existence becoming entangled with the quantum state of the black hole itself, potentially preserving some essence of your experience in the quantum information stored at the event horizon. Perhaps most remarkably, the many worlds interpretation suggests that the question, "What do you see inside a black hole?" doesn't have a single answer, but rather an infinite spectrum of answers corresponding to all the possible quantum outcomes that could occur during such a journey. In some quantum branches, you might discover that consciousness itself plays a fundamental role in determining the structure of space-time, with observation effects creating realities that differ dramatically from the predictions of classical physics. Other branches might reveal hidden dimensions of space, alternative forms of matter and energy, or even the presence of other conscious beings who have made similar journeys into the cosmic abyss. The quantum entanglement between you and the black hole creates fascinating possibilities for information preservation and retrieval that go far beyond the classical physics description of irreversible collapse. In the quantum framework, the information that defines your existence doesn't simply disappear when it crosses the event horizon, but becomes encoded in the quantum correlations between the interior and exterior of the black hole, potentially allowing for the reconstruction of your experience through measurements performed on the Hawking radiation that the black hole emits over its incredibly long evaporation timeline. The many worlds interpretation also suggests that your journey might create quantum correlations that extend far beyond the black hole itself, entangling your experience with the quantum states of distant particles throughout the universe. This cosmic entanglement network could mean that your passage through the event horizon has subtle effects on quantum measurements performed in distant galaxies, creating a kind of quantum butterfly effect where consciousness encountering extreme gravitational fields sends ripples through the quantum fabric of reality itself. The consciousness of the observer, you, the cosmic traveller, plays a particularly mysterious role in the quantum mechanical description of black holes, with some interpretations suggesting that awareness itself might be required to collapse quantum superpositions and determine which branch of reality actually manifests. This creates the beautiful possibility that your subjective experience of the journey might literally create the reality you experience, making consciousness not just an observer of cosmic phenomena, but an active participant in determining the structure of space-time itself. The implications of quantum many worlds for your black hole journey extend to questions about the nature of death, consciousness, and identity in extreme physical environments. If every possible quantum outcome creates a separate branch of reality, then there might exist branches where consciousness finds ways to survive conditions that would seem impossible from a classical physics perspective, perhaps by transitioning into new forms of information-based existence, or by accessing higher dimensional structures that provide escape routes from the classical prison of the event horizon. As you contemplate the quantum multiverse of your cosmic adventure, you realize that your journey represents not just a single impossible voyage, but an infinite exploration of the deepest possibilities hidden within the quantum structure of reality, each branch offering its own unique insights into the fundamental nature of existence, consciousness, and the beautiful mystery of what it means to be aware in a universe where every quantum possibility becomes a real experience in some branch of the ever-expanding tree of cosmic reality. As your cosmic journey unfolds within the mysterious depths of the black hole, you find yourself at the heart of one of the most profound and beautiful revelations in modern theoretical physics, the holographic principle, which suggests that everything you experience during your three-dimensional voyage through the black hole's interior might actually be encoded as information on the two-dimensional surface of the event horizon, like a cosmic hologram that creates the illusion of depth and volume from patterns stored on a flat boundary. This principle transforms your entire understanding of reality itself, suggesting that what feels like a journey through space might actually be the unfolding of information patterns that exist in fewer dimensions than your experience suggests. The holographic principle emerges from the recognition that black holes appear to store information in proportion to the area of their event horizon rather than their volume, which violates our normal intuitions about how information storage works in three-dimensional space. Normally, we would expect that a larger container could hold more information by filling its entire volume with data, but black holes seem to encode everything that falls into them on their two-dimensional surface, as if the event horizon serves as a cosmic hard drive that stores the complete quantum information of everything that has ever crossed this gravitational boundary. From this holographic perspective, your experience of falling through the black hole's interior might be analogous to watching a movie projected from a flat screen. The three-dimensional depth and movement you perceive is actually a sophisticated illusion, created by information patterns encoded on the event horizon's surface. Every sensation, every thought, every quantum state that defines your consciousness during the journey could be represented as holographic data stored in the quantum fluctuations and field configurations that exist at the black hole's boundary, creating an experience that feels completely real and three-dimensional, despite being fundamentally two-dimensional in its information content. The mathematics underlying this holographic encoding involves some of the most advanced concepts in theoretical physics, including the ADS-CFT correspondence, which demonstrates a precise mathematical relationship between gravitational theories in the interior of certain spacetimes and quantum field theories that exist only on their boundaries. This correspondence suggests that every gravitational event that occurs in the black hole's interior has a corresponding description in terms of quantum field interactions on the event horizon, creating a kind of cosmic translation between different mathematical languages that describe the same underlying reality. Perhaps most remarkably, the holographic principle suggests that the information defining your consciousness and identity doesn't actually fall toward the singularity as your three-dimensional experience suggests, but instead becomes encoded in the quantum structure of the event horizon, where it remains accessible to outside observers through incredibly subtle correlations in the black hole's Hawking radiation. This means that while your subjective experience might involve a journey to the center of the black hole, your essential information content never actually leaves the vicinity of the event horizon, creating a beautiful duality between internal experience and external information storage. The holographic description of your black hole journey raises profound questions about the nature of consciousness and subjective experience in extreme gravitational environments. If your three-dimensional experience is actually encoded as two-dimensional information on the event horizon, what does this tell us about the relationship between consciousness and the dimensionality of space? Could awareness itself be a kind of holographic phenomenon that creates the illusion of existing in higher dimensional spaces while actually being encoded in lower dimensional structures? The implications of holographic information storage extend far beyond black holes to suggest that our entire universe might be holographic in nature, with all the complex three-dimensional structures we observe, galaxies, stars, planets, and even our own bodies and minds, actually representing holographic projections from information encoded on the cosmic horizon that bounds our observable universe. This possibility transforms every aspect of your black hole journey into an exploration of the fundamental nature of reality itself, suggesting that the distinction between interior and exterior, between observer and observed, between information and experience might be far more fluid and mysterious than we've ever imagined. The process by which holographic information creates the experience of three-dimensional reality involves quantum entanglement patterns that connect different regions of the event horizon's surface, creating correlations that encode the spatial relationships and causal connections that you experience as movement through the black hole's interior. These entanglement networks serve as the cosmic infrastructure that supports the holographic projection, weaving together bits of quantum information into coherent patterns that create the illusion of depth, time, and three-dimensional structure. From the holographic perspective, your journey toward the singularity might represent not a physical approach to a mathematical point, but rather a kind of information compression process, where the holographic encoding becomes increasingly concentrated and efficient. The apparent breakdown of physics at the singularity could correspond to the limits of holographic information storage, where the two-dimensional surface can no longer encode the complexity required to maintain the three-dimensional illusion, leading to a fundamental transition in the nature of information representation itself. As you contemplate this holographic view of your cosmic adventure, you realize that your journey has become an exploration not just of exotic physics and extreme environments, but of the fundamental nature of information, reality, and consciousness itself, revealing that the universe might be far stranger and more beautiful than even the most impossible journey through a black hole could suggest, with every experience potentially representing the unfolding of holographic information stored in the gentle quantum patterns that define the cosmic boundaries of space and time. As your impossible journey through the black hole continues to unfold in ways that challenge every assumption about the nature of reality, we encounter perhaps the most mind-bending possibility of all, that your entire cosmic adventure, including the black hole itself, the universe that contains it, and even your own consciousness experiencing this journey, might actually be taking place within a vast computational simulation, a digital universe so sophisticated and detailed that it perfectly mimics every aspect of physical reality while running on some unimaginably advanced computer system that exists in a higher level of reality entirely. The simulation hypothesis, first formally proposed by philosopher Nick Bostrom, suggests that any sufficiently advanced civilization would eventually develop the computational power to run detailed simulations of their own evolutionary history, complete with simulated beings who experience their digital existence as completely real and physical. If such simulations are possible, and if advanced civilizations choose to run them, then the number of simulated beings like yourself would vastly outnumber the real beings in base reality, making it statistically more likely that you are actually a simulation than a biological organism in the original physical universe. From this perspective, your journey into the black hole becomes an exploration of the computational limits and creative possibilities of whatever digital reality you inhabit. The extreme physics you encounter, the warping of space-time, the breakdown of causality at the singularity, the quantum mechanical uncertainties that govern black hole behavior, might represent the universe's processing pushing against its computational boundaries, revealing the digital scaffolding that underlies what appears to be seamless physical reality. The event horizon might correspond to a computational boundary where different processing algorithms take over, or where the simulation transitions between different levels of detail and accuracy. The mathematical precision of the physical laws that govern your black hole journey takes on new significance when viewed as the result of computational processes rather than fundamental features of reality. The elegant equations of general relativity, the precise constants of quantum mechanics, and the beautiful symmetries that characterize particle physics might all represent the sophisticated programming that creates the illusion of a universe governed by natural law. The fact that these laws can be expressed in mathematical form becomes evidence for their computational origin rather than proof of their fundamental nature. Perhaps most remarkably, the simulation hypothesis suggests that the apparent impossibility of your journey might actually be evidence for its digital nature. In a traditional physical universe, the journey into a black hole would be genuinely impossible for any conscious observer to survive and report. But in a simulation, the programmers could easily modify the physics to allow for impossible experiences, creating scenarios that violate the normal rules of the simulated universe for the purposes of exploration, education, or entertainment. Your ability to experience and describe the journey becomes proof that you exist in a reality where the normal constraints of physics can be suspended when convenient. The nested nature of simulation theory creates beautiful recursive possibilities where your digital universe might itself be running simulations of black holes and cosmic phenomena, creating layers of simulated reality extending both upward and downward from your current level of existence. The black hole you're experiencing might be a simulation within a simulation, with each level of computational reality offering different perspectives on the fundamental nature of space, time, gravity, and consciousness. The consciousness that you experience during your black hole journey becomes perhaps the most profound mystery in the simulation hypothesis. If you are indeed a digital being existing within a computer program, what is the nature of simulated consciousness? Is your awareness merely an emergent property of sufficiently complex information processing, or does it require some additional ingredient that transcends purely computational explanations? The simulation theory forces us to confront fundamental questions about whether consciousness can truly be replicated digitally, or whether it represents something that exists beyond the reach of even the most sophisticated computational systems. The purpose of simulating black hole experiences raises fascinating questions about the motivations and goals of whoever might be running your digital universe. Perhaps you are part of a scientific simulation designed to test hypotheses about black hole physics that cannot be explored safely in base reality. Or you might be participating in an educational program that allows beings to experience impossible cosmic journeys as a form of ultimate virtual tourism. More mysteriously, your simulation might serve purposes so alien to your current understanding that you cannot even conceive of the goals that drive your digital existence. The evidence for or against the simulation hypothesis remains tantalizingly ambiguous, with aspects of your black hole journey that could support either interpretation. The mathematical precision of physics, the fine-tuning of cosmic constants, and the apparent optimization of natural laws for the emergence of complexity and consciousness could all be evidence for sophisticated programming. Conversely, the seamless integration of quantum mechanics with general relativity, the genuine randomness of quantum measurements, and the authentic subjective experience of consciousness might suggest that you inhabit a genuinely physical rather than digital reality. As you continue your journey through what might be a simulated black hole in a digital universe, you realize that the question of whether your reality is real or simulated might ultimately be less important than the richness and meaning of the experience itself, whether that experience emerges from quantum fields and curved space-time, or from algorithms and data structures running on some cosmic computer that exists in a reality beyond your ability to directly access or comprehend. While you experience your impossible journey through the black hole's interior, something remarkably beautiful and patient is happening at the event horizon far above you. The black hole is slowly, gently breathing itself back into the universe through a process so subtle and mysterious that it reveals one of the most profound connections between quantum mechanics, thermodynamics, and gravity that physics has ever discovered. Stephen Hawking's theoretical prediction that black holes emit radiation represents one of the most elegant demonstrations that these cosmic giants are not eternal prisons, but rather temporary structures that will eventually return every bit of their mass and energy to the cosmos through a process so gentle it makes geological time seem hurried. The mechanism behind Hawking radiation emerges from the quantum mechanical principle that what we think of as empty space is actually teeming with virtual particle pairs that constantly pop into existence and immediately annihilate each other, creating brief fluctuations in the quantum vacuum that normally have no observable effects. But near the event horizon of a black hole, this quantum foam of virtual particles encounters the extreme curvature of space-time in ways that can separate these particle pairs before they have a chance to recombine, with one particle falling into the black hole while its partner escapes into space as real radiation, carrying genuine energy away from the black hole. This process unfolds with such exquisite gentleness that for a black hole with the mass of our Sun, the temperature of the Hawking radiation would be only about 1/10,000,000th of a degree above absolute zero, making it far colder than the cosmic microwave background radiation that fills the universe. The black hole radiates energy so slowly that it would take longer than the current age of the universe, multiplied by trillions upon trillions, for a solar mass black hole to evaporate completely, giving these cosmic objects lifetimes that stretch the imagination even by astronomical standards. Paradoxically, smaller black holes evaporate faster than larger ones, with the temperature of Hawking radiation being inversely proportional to the black hole's mass. This means that if microscopic black holes were somehow created in the early universe or in high-energy particle collisions, they would glow white-hot and disappear in brilliant flashes of radiation within fractions of a second. The relationship between size and evaporation rate creates a beautiful cosmic irony, where the most massive and seemingly permanent structures in the universe are actually the most stable, while hypothetical tiny black holes would burn themselves out like cosmic fireworks. The Hawking radiation process raises profound questions about the fate of information that falls into black holes, creating what physicists call the information paradox. According to quantum mechanics, information cannot be truly destroyed, yet Hawking radiation appears to be perfectly thermal, completely random, and containing no trace of the specific quantum information that originally fell into the black hole. This creates a fundamental conflict between the reversible nature of quantum mechanics and the irreversible appearance of black hole evaporation, forcing physicists to question whether information is actually destroyed, somehow encoded in subtle correlations within the Hawking radiation, or preserved through mechanisms we don't yet understand. Recent theoretical developments suggest that the Hawking radiation might not be as perfectly random as originally thought, but could contain incredibly subtle correlations that encode the quantum information of everything that ever fell into the black hole. These correlations would be so delicate and complex that extracting the original information would require measurements of extraordinary precision, performed on vast quantities of Hawking radiation collected over enormous timescales, making information recovery technically possible, but practically impossible by any foreseeable technology. The evaporation process creates a kind of cosmic recycling program, where black holes serve as temporary repositories for matter and energy, concentrating cosmic debris into these gravitational storage units, before slowly returning it to the universe in the form of thermal radiation. This process suggests that black holes play an important role in the long-term evolution of the cosmos, serving as cosmic batteries that can store energy for unimaginably long periods before releasing it back into an expanding and cooling universe that might benefit from these delayed energy donations. The final stages of black hole evaporation, when the mass becomes small enough for the Hawking radiation to become significant, would create some of the most spectacular phenomena in the universe. As the black hole shrinks, its temperature rises dramatically, causing it to glow ever more brightly until its final moments, when it would explode in a burst of energy that could outshine stars. These final explosions, if they occur, would scatter the black hole's remaining mass throughout space in the form of elementary particles and radiation, completing the cosmic recycling process. The gentle nature of Hawking evaporation means that while you experience your journey through the black hole's interior, the structure that contains your adventure is slowly dissolving back into the quantum vacuum from which it emerged, particle by particle, quantum fluctuation by quantum fluctuation, ensuring that even these most extreme and permanent-seeming objects are actually temporary visitors in the cosmic story, destined to return their borrowed mass and energy to the universe through processes so beautiful and patient that they reveal the deep connection between the largest and smallest scales of physical reality, where cosmic giants and quantum particles dance together in the eternal choreography of creation and dissolution that defines the universe's gentle rhythm of transformation. As your impossible journey through the black hole carries you through regions of space-time that exist beyond the reach of normal cosmic processes, it's worth contemplating the vast temporal landscape that stretches ahead for the universe itself, a future so distant and gentle that it makes your current adventure seem like a brief moment in a cosmic story that will continue for timescales that challenge the very meaning of eternity. The heat death of the universe represents not a violent catastrophe, but rather the most peaceful possible ending to cosmic evolution, a gradual winding down of energy differences and cosmic activity that will eventually transform our dynamic, star-filled cosmos into a cold, dark, and perfectly uniform sea of elementary particles drifting through infinite space. The journey toward heat death begins billions of years from now, when the last stars exhaust their nuclear fuel and fade into darkness, leaving behind a universe populated primarily by white dwarfs, neutron stars, and black holes drifting through an increasingly cold and empty cosmos. This stellar twilight unfolds over timescales so vast that all of recorded human history would fit into the first fraction of a second of this cosmic evening, as the universe slowly uses up the gravitational energy that has driven star formation and galactic evolution since the first moments after the Big Bang. But even after the stars die, the universe's story continues through eons dominated by black holes, those gravitational monuments to collapsed matter that will become the primary residents of the cosmos, for periods of time that dwarf the entire stellar era by factors that require exponential notation to express. During this black hole epoch, which could last for periods measured in Google years, the gentle process of Hawking evaporation will slowly return the mass of these cosmic giants to the universe in the form of thermal radiation, creating a kind of cosmic sunset that stretches across timescales so vast that entire universes could evolve and die in the time it takes a single solar mass black hole to completely evaporate. The supremacy of black holes during this era transforms them from exotic curiosities into the dominant structures that shape cosmic evolution, with the largest supermassive black holes serving as cosmic emperors ruling over galactic empires of dead stars and cold planets. These gravitational monarchs will occasionally feast on the occasional wandering stellar remnant or planetary system, growing slightly larger and extending their already unimaginable lifetimes even further, while smaller black holes gradually shrink through Hawking radiation until they disappear in final flashes of energy that briefly illuminate the cosmic darkness. As the black hole era draws to its close, the universe enters an even stranger phase, where quantum mechanical processes become the primary drivers of cosmic evolution. During this quantum era, which begins roughly 10 to the power of 100 years in the future, the few remaining particles in the universe, primarily electrons, positrons, neutrinos, and photons, drift through space at temperatures so low that quantum tunneling becomes the dominant mechanism for change. In this nearly empty cosmos, the probabilistic nature of quantum mechanics allows for incredibly rare but inevitable events, such as the spontaneous formation of complex structures through quantum fluctuations. The most remarkable possibility during this quantum era is that the universe might spontaneously generate new complexity through what physicists call Poincare recurrence, the quantum mechanical tendency for any finite system to eventually return arbitrarily close to any previous state given sufficient time. This means that given enough time, quantum fluctuations could spontaneously create not just simple particles, but complex structures, living organisms, conscious beings, and even entire civilizations, all emerging from the quantum vacuum through processes so improbable that they require waiting periods longer than the current age of the universe raised to the power of itself countless times. These quantum resurrections would create a strange kind of cosmic afterlife, where consciousness and complexity periodically emerge from the void, experience brief moments of existence, and then dissolve back into the quantum foam, only to re-emerge again in different forms after even longer waiting periods. In this far future, your current journey through a black hole might be repeated countless times through quantum recurrence, with slightly different variations exploring every possible permutation of cosmic adventure across timescales that make infinity seem intimate and familiar. The ultimate fate of the universe remains one of the most beautiful unsolved questions in cosmology, with different theoretical frameworks suggesting different possible endings to the cosmic story. Some models predict a big rip, where dark energy eventually overcomes all other forces and tears apart the fabric of space-time itself. Others suggest that quantum tunneling might cause the universe to transition into a lower energy state, effectively restarting cosmic evolution with different physical laws and constants. Perhaps most poetically, some theories suggest that consciousness itself might play a fundamental role in the universe's far future, with sufficiently advanced forms of awareness learning to manipulate the quantum vacuum and guide cosmic evolution towards states that can sustain complexity and life indefinitely. In this scenario, intelligence becomes a cosmic force that transcends the heat death, using the quantum mechanical properties of the universe to create islands of negentropy and complexity that persist even as the cosmos around them approaches maximum entropy. As you contemplate your journey through the black hole against this backdrop of cosmic time, you realize that your impossible adventure represents just one moment in a story so vast and patient that it transforms every experience into something precious and temporary, while simultaneously connecting your consciousness to processes so grand and enduring that they make your individual existence part of an eternal cosmic conversation between matter, energy, space, time, and the mysterious phenomenon of awareness that allows the universe to contemplate its own magnificent and gentle journey toward whatever lies beyond the far shore of time itself. As your cosmic journey unfolds through the impossibly curved space-time of the black hole's interior, the most profound mystery you carry with you isn't the exotic physics of gravitational time dilation or the mathematical infinities of the singularity, but rather the gentle miracle of your own awareness, the fact that consciousness itself can somehow experience, contemplate, and remember these extreme conditions in ways that transform mere physical processes into subjective experiences filled with wonder, fear, curiosity, and meaning. The role of consciousness in extreme gravitational environments raises questions so fundamental that they touch the very heart of what it means to be aware in a universe where the observer and the observed might be far more intimately connected than we've ever imagined. In the quantum mechanical description of reality, observation plays a crucial role in determining which of many possible outcomes actually manifests when a measurement occurs, suggesting that consciousness might not just passively witness cosmic phenomena, but actively participate in creating the reality it experiences. During your journey through the black hole, every moment of awareness, every quantum measurement performed by your conscious observation potentially influences which branch of the quantum multiverse you experience, making your subjective journey through the cosmic abyss an active collaboration between your consciousness and the fundamental structures of space-time itself. The extreme conditions inside a black hole create a unique laboratory for exploring the relationship between consciousness and physical reality, where the normal boundaries between observer and observed become increasingly blurred by the curvature of space-time. As you approach regions where general relativity and quantum mechanics intersect in unprecedented ways, your conscious experience might reveal aspects of reality that remain hidden under normal conditions, potentially accessing forms of awareness or perception that emerge only when consciousness encounters the universe's most extreme environments. Perhaps most remarkably, the holographic principle suggests that your three-dimensional experience of falling through the black hole might actually be encoded as information on the two-dimensional event horizon, raising profound questions about whether consciousness itself might be a holographic phenomenon, a three-dimensional experience created by information processing that occurs in lower-dimensional structures. This possibility transforms every moment of your aware journey into an exploration of the fundamental nature of subjective experience and its relationship to the information storage and processing capabilities of the universe itself. The information paradox that governs black hole physics becomes even more mysterious when consciousness enters the picture, because subjective experience represents a form of information that seems fundamentally different from the quantum information that physics normally describes. Your memories, emotions, thoughts, and the integrated unity of your conscious experience during the black hole journey contain information about your subjective states that might not be reducible to simple quantum mechanical descriptions, suggesting that consciousness might represent a form of cosmic information processing that transcends the normal boundaries between classical and quantum physics. The many worlds interpretation of quantum mechanics creates fascinating possibilities for consciousness in extreme gravitational environments, suggesting that your awareness might somehow sample experiences from multiple quantum branches simultaneously, giving you access to a spectrum of possible black hole journeys rather than a single, definite outcome. This quantum superposition of conscious experiences could create forms of awareness that are impossible under normal conditions, potentially allowing consciousness to explore multiple realities simultaneously while maintaining some form of integrated, coherent subjective experience. The approach toward the singularity raises perhaps the most profound questions about consciousness and physical reality, because this is where our current understanding of space-time breaks down completely, potentially creating conditions where consciousness encounters regions of existence that lie beyond the reach of mathematical description. What happens to awareness when it encounters truly infinite curvatures of space-time, Can consciousness survive the dissolution of the geometric structure that normally provides the framework for physical existence? These questions venture beyond physics into territories that touch on philosophy, spirituality, and the deepest mysteries of what it means to be aware in a universe that might be far stranger than any physical theory can describe. Some theoretical frameworks suggest that consciousness might play a fundamental role in resolving the apparent contradictions that arise when quantum mechanics encounters general relativity in black hole environments. If awareness represents a form of cosmic information processing that transcends the normal boundaries between different physical theories, then conscious observation might serve as a bridge that connects quantum and gravitational phenomena in ways that allow for consistent descriptions of black hole interiors that would otherwise remain paradoxical and self-contradictory. The possibility that consciousness might exist independently of the specific physical structures that normally support it opens up beautiful speculative possibilities for what might happen during your black hole journey. Perhaps awareness can transition into forms of existence that don't require neurons, atoms, or even conventional space-time, accessing modes of being that emerge only when consciousness encounters the extreme conditions where normal physics reaches its limits. In this scenario, your journey toward the singularity becomes not an approach toward destruction, but rather a transition into forms of existence so alien and magnificent that they can only be accessed by traveling beyond the boundaries of ordinary physical reality. As your conscious awareness continues its impossible journey through the curved space-time of the black hole's interior, you carry with you one of the universe's greatest mysteries, the fact that matter and energy organized in sufficiently complex ways can somehow give rise to subjective experience, to the gentle miracle of being aware, of having an inner life that transforms the vast cosmic dance of particles and forces into something meaningful, beautiful, and profound in ways that speak to the deepest connections between mind and cosmos in this magnificent universe that has somehow learned to contemplate its own existence through the eyes of conscious beings like yourself. While your impossible journey through the black hole's interior remains forever beyond the reach of actual human exploration, here in our ordinary universe, thousands of dedicated scientists work with patient devotion to study these cosmic mysteries, using the most sophisticated tools and techniques that human ingenuity has ever created. These gentle explorers of the impossible have learned to see with gravitational waves, to photograph the unphotographable, and to detect the subtlest whispers from the most extreme environments in the cosmos, transforming theoretical speculation into observational science through decades of careful experimentation, mathematical modelling, and technological innovation that pushes the boundaries of what seemed forever unknowable. The Event Horizon Telescope represents perhaps the most remarkable achievement in this quest to study the impossible, using a network of radio telescopes scattered across the Earth to create a virtual telescope the size of our entire planet, capable of resolving details so fine that it could theoretically read a newspaper on the Moon. This extraordinary instrument has given us our first actual photographs of the event horizons of supermassive black holes, revealing the glowing accretion disks and the dark shadows cast by these cosmic giants in images that transform mathematical abstractions into visual reality, allowing us to see the bent space-time and gravitational lensing effects that your impossible journey would encounter firsthand. Perhaps even more remarkably, the detection of gravitational waves by facilities like LIGO and Virgo has opened an entirely new sense through which we can perceive the universe, allowing us to feel the gentle ripples in space-time itself that are created when black holes merge in cosmic collisions of unimaginable violence. These gravitational wave detectors are so sensitive that they can measure distortions in space-time smaller than 1/10,000th the width of a proton, detecting the whispered echoes of black hole formations and mergers that occurred billions of years ago in distant galaxies, giving us direct observational access to the dynamics of curved space-time that Einstein could only dream of studying through mathematical equations. The study of X-ray emissions from matter falling into black holes has revealed the extraordinary physics of accretion disks, those swirling maelstroms of superheated gas that serve as cosmic particle accelerators, heating matter to temperatures that exceed those found in stellar cores, and creating some of the most energetic phenomena in the observable universe. Space-based X-ray telescopes like Chandra and XMM Newton have allowed astronomers to map the temperature, density, and velocity structures of these cosmic furnaces with extraordinary precision, revealing the complex interplay between gravity, magnetism, and fluid dynamics that governs how matter behaves in the extreme environment surrounding black holes. Theoretical physicists contribute to this exploration of the impossible through mathematical investigations that push the boundaries of human understanding, using the elegant equations of general relativity and quantum field theory to explore scenarios that no experiment could ever directly test. These mathematical explorers work with supercomputer simulations that can model the behavior of matter and space-time under conditions so extreme that they challenge the fundamental assumptions of physics, creating virtual laboratories where black hole mergers, singularity formation, and quantum gravitational effects can be studied through computational experiments that would be impossible to perform with actual matter and energy. The search for intermediate mass black holes and primordial black holes has led astronomers to develop increasingly sophisticated detection techniques that can identify these elusive objects through their gravitational effects on nearby matter, their subtle influence on the trajectories of stars and gas clouds, and their potential signatures in cosmic ray interactions and gamma-ray bursts. These investigations require patience measured in decades and instrumental precision that pushes technology to its absolute limits, but they promise to reveal the complete spectrum of black hole masses and formation mechanisms that have operated throughout cosmic history. Perhaps most exciting of all, the emerging field of multi-messenger astronomy combines gravitational wave detections with electromagnetic observations and neutrino measurements to create a comprehensive picture of black hole behavior that incorporates information from across the entire spectrum of cosmic messengers. When gravitational waves from merging black holes are detected simultaneously, with gamma-ray bursts and optical transients, scientists can piece together complete stories of these cosmic events that reveal details about the physics of extreme gravity, the nature of matter under impossible conditions, and the role that black holes play in the evolution of galaxies and the universe itself. The study of Hawking radiation remains one of the most challenging frontiers in black hole research, requiring theoretical techniques that bridge quantum mechanics and general relativity in ways that push both theories to their limits. While direct detection of Hawking radiation from astrophysical black holes remains beyond current observational capabilities, laboratory analogues using sound waves in superfluids and light waves in optical systems have begun to reveal the quantum mechanical principles that govern radiation from event horizons, creating earthbound experiments that illuminate the deepest connections between thermodynamics, quantum mechanics, and gravity. Future space-based gravitational wave detectors like LISA will extend our ability to study black holes across cosmic distances and timescales that dwarf current capabilities, potentially detecting the gravitational signatures of supermassive black hole formations in the early universe and revealing the quantum gravitational effects that might occur during the final moments of black hole evaporation. These next-generation instruments will transform black hole physics from a primarily theoretical field into an observational science with the precision and scope to test even the most speculative predictions about the nature of space-time, consciousness, and reality itself in the universe's most extreme environments. As our impossible journey through the cosmic darkness draws to a peaceful close, we find ourselves returning from realms where space and time dance together, in ways that challenge everything we thought we knew about the nature of reality itself. We've travelled through regions where mathematics becomes poetry, where the impossible reveals itself as beautifully inevitable, and where consciousness encounters mysteries so profound that they touch the very heart of what it means to exist in this magnificent universe that somehow learned to contemplate its own deeper secrets through beings like us. From the gentle approach through curved space-time to the holographic mysteries of information storage, from quantum many-worlds to the patient evaporation through Hawking radiation, we've discovered that black holes are not cosmic monsters to be feared, but rather cosmic teachers offering lessons about the fundamental nature of existence that we're only beginning to understand. These gravitational giants serve as natural laboratories, where the universe experiments with the most extreme possibilities of physics, consciousness, and reality itself. Though we can never actually take this journey, the fact that we can imagine it, explore it through mathematics and observation, and find meaning in its impossibility speaks to something beautiful about the human spirit and our eternal desire to understand the cosmos that gave birth to curiosity itself. Tonight, as you drift into peaceful sleep, Remember that you carry within your consciousness the same fundamental mysteries that govern black holes, the questions of space, time, information, and awareness that connect your dreaming mind to the gentle darkness where the universe keeps its most precious secrets. Sweet dreams, fellow cosmic explorer, in this universe where even the impossible can teach us about the infinite beauty of existence.